Rebirth of Plastics, Converting Polypropylene and Polyethylene into Useful Olefins by Erica Matheson, J.C. Butler, Peyton Musselman, and Vivian Newell.
For our challenge problem, we chose to model a new catalytic process created and published by a group of UC Berkeley students. Their process breaks down polypropylene and polyethylene plastics into their monomer counterparts, olefins. This is done using a semi-batch reactor and a continuous flow with catalysts. For our analysis of the process, we will be looking at the shifting of the average molecular weight over time and how this affects the viscosity of the mixture. Our goal with modeling this problem is to estimate how viscosity changes with the changing of molecular weight. We estimate as the reaction progresses that the average molecular weight of the polypropylene and polyethylene will decrease until there are a majority of olefins in the mixture. As the concentration of the olefins increases, we assume that the viscosity of the mixture will also decrease. We will use the population balances and the Mark-Huink equation to show this.
Several groups of researchers have studied ways to break down or reuse plastics, but most of these proposed methods are not energy efficient and the materials needed are too costly. Researchers recently discovered that introducing fresh ethylene with the right catalyst can transform polyolefins back into their respective building blocks. Students at UC Berkeley have found that the process works using a more abundant combination of catalysts, being sodium and tungsten oxide. While the students have modeled and proved the viability of the reaction process, they have yet to make an economic analysis of performing it on an industrial scale. This reaction process begins with diluting long-chain polymers, polypropylene and polyethylene with ethylene. They are then broken down into monomers, propylene and isobutylene, through catalytic cracking. The catalysts used are tungsten oxide on silica and sodium metal on alumina. The sodium catalyst is selective for polyethylene, and the tungsten oxide catalyst is selective for polypropylene and will react only with the polymer they are selective for until there is none left of their preferred polymers. The catalysts break a bond on the ends of the polymer chain and continue to break bonds until just monomers are left.
By modeling the breakdown of plastics and the associated viscosities of the polypropylene and polyethylene mixture, we are better able to understand the energy that will be required to run the reactor. It is assumed that with a decrease in viscosity, mixing becomes easier and the amount of power required to stir the mixture lessens. As less power input is required, the energy consumed by the process is reduced. In the model created by the UC Berkeley students, energy consumption will play a role in the feasibility of upscaling the process to an industrial scale. The energy expenditure will contribute to the overall cost of manufacturing of plastic olefins. To assess the feasibility of upscaling this process, we focus on modeling the molecular weights with population balances and change in viscosity over time.
To further simplify things, other assumptions regarding the reaction need to be made. We assumed that the reactor is adiabatic and isobaric. The reaction continues to completion, and the average starting molecular weight is 1 million gram moles.
The population balances were determined from a variety of assumptions and conditions of the process. We started with a molecular weight of 1 million and wrote coupled population balance equations until the molecular weight could no longer be halved and still be big enough for our olefin with a molecular weight of 42. It was assumed that the concentration of one molecular weight is equal to the amount of the next highest in the previous equation minus 2K of the current molecular weight. After writing out all of the population balance equations, we use state space form to solve further. We can do this because they are coupled ODEs with initial values. The initial values we are using to solve this are 1 for the first equation and 0 for the others. This is done because we are assuming that we have polymers of 1 million molecular weight and none smaller than that when the reaction starts. After using state space form, we use the MATLAB solver ODE45, which is a Runge cut of 4 method combined with a Runge cut of 5. Plotting this will give us the concentration of the different populations over time. The values of the reaction constant K are relative. This is because for both polyethylene and polypropylene, the population balances are the same, but with different K values. This trend with the concentration graphs and molecular weight over time makes it so the equations don't need to be modeled twice for polypropylene and polyethylene, respectively.
We decided to use the Mark-Huink equation for calculating the viscosity change over time and over molecular weight. The constants for the equation we estimated from an appendix of Mark-Huink parameters. None of the constants were quite right, but they were the closest approximation to our reaction. In an attempt to have the high temperature be taken into account, the parameters were raised. The raised parameters and the initial parameters were all plotted on the same graph to see the degree of which the parameters changed. We found that our results supported our hypothesis and show similar trends to what was given in the UC Berkeley paper. As the reaction progresses, the molecular weights exhibit a bell curve shape except for the starting molecular weight of the polypropylene and the polyethylene and the ending molecular weight of the monomers. The polymers show a steep decrease in concentration as they react, and the monomers show an exponential increase as time progresses until the solution is fully reacted. The viscosity of the solution also shows a sharp decrease as time progresses and as the molecular weight decreases, although the altered parameters meant to account for the higher temperature behave differently than expected. We would have expected that with a higher temperature, the viscosity would decrease, but instead it increased. This is likely due to error in the approximations. For more accurate results, better Mark-Hewing parameters need to be used.
Thinking back to the initial goal of our challenge project, it appears that the power required would be extremely high in order for this reaction to go to completion. The reaction is time-intensive and the viscosity of the solution remains high for most of the reaction. To stir a reactor like this for a substantial amount of time would prove to be costly due to the energy consumption required to power the mixer, which calls into question the feasibility of upscaling the process to an industrial scale. In order to keep the recycling plant active, significant funds would need to be allocated to just the breakdown of plastics. The exact amount of power and funds required were not calculated due to the scope of this model. Further research is advised. Additionally, improvements to the model found could be improved with more research, such as the use of more accurate viscosity models and in-lab testing. Research was limited due to resources available and access to similar studies, which resulted in the mathematical model and little to no corroborating experimental data.
This project helped us better understand how to apply equations and techniques ones learn in class and outside of class to real-world applications, though we faced a few obstacles on the way. As this research topic is so recent in the scientific community, we only had one resource to take numbers from, meaning what we could do was very constrained. In the future, a research topic with more background knowledge and existing parameter calculations would have been a preferred pick for this challenge problem, as we could have increased complexity without needing to make excessive assumptions, sacrificing accuracy.